Hello and welcome to lecture 15 of the course on quantum entanglement and non-local games. I am Dhiraj and today we look at the definition of compound register. So in the last lecture we had discussed what is actually a quantum state, how does it evolve, and what it means to make a POVM measurement. Now we will move on and we look at the definition of compound registers. So by compound registers, what I mean is that if you have a state on a register A and another state on a register B, then what does it look if you have a compound state on A and B? So let's see. So suppose if A and B are two C star algebraic registers with C star algebra A and B, we can look at the compound register A comma B. So what does it mean, right, to have a compound register? Right? So basically we'll first need to define an algebra on A tensor B, so that we'll see now. So in order to do that, we consider a C star algebra which is the completion of algebra generated by A tensor B, all these tensor products with A in A and B in B. So first we take all the tensor products, then we consider the algebra generated by these tensor products, right? So which consists of all the linear combination of these AI tensor BIs. Once we have all those linear combination, then we take the completion, right? So if you only take all the linear combinations, you will get A tensor B, but we don't just want that. It should be a complete sort of a metric space under a norm, right? So under some norm for A tensor B. Now how do we define a norm for A tensor B? So what we'll do is that we'll use min norm, and that will give us a min tensor product. So that gives a sort of a min tensor product. Now how do we define this min norm? So for C star algebras, A and B, define the min norm A tensor B as for any x in tensor B, what we have is that the min norm of x is the supremum of pi A tensor pi B x, where pi A is a isomorphism from A to a bounded Hilbert space HA, a bounded operators on Hilbert space HA, and pi B is a star homomorphism from B to bounded Hilbert space on B, right? So where pi A tensor pi B from A to B bounded space, space of bounded operators on HA tensor HB is a star homomorphism. Right. So by the GNS theorem, So this supremum is over a non-empty set. Okay, why is it so? Because GNS theorem guarantees us that like for any C star algebra, there is an mapping to some, like there is an isomorphism to some bounded space of Hilbert operators. So basically there is at least some sort of mapping, and then we are taking the supremum over all these mappings, the norm of pi A tensor pi b x, and this norm is called as the min norm. Okay, so there is something called as max norm also that we will not need today. And basically now the states on basically the registers A and B are those states which are defined over this particular set of completion of A star B. So basically we have defined this norm. This norm will actually allow us to define a completion of A tensor B. This completion of A tensor B refers to our C star algebraic sort of C star algebra, the new C star algebra we have over the two registers put together, and the states on these C star algebras are linear functionals from elements of these algebra to C. And now we come to the notion of a product state. So given abstract states, SA from A to C and SB from B to C. So we define product state SA tensor SB from A tensor min B to C as SA tensor SB A tensor B equals to SAA times SBB. So we can now extend this to A tensor min B by linearity and continuity of S. Now we come to the notion of localized reversible operations. Suppose A and B are registers with C star algebras A and B. Let S from A tensor min B to C be a state on A comma B. Let pi from A to A be a star automorphism representing reversible operations on A. Then we can extend pi to pi tensor I by, so this pi tensor I is a mapping from A tensor min B to A tensor min B as pi tensor I A tensor B equals pi A tensor B for all A in A and B in B. So basically the thing is that if I only have an operation which acts on my first register, then I can extend it to an operation on the combined register, and the idea is that it will act like identity on the other register, right? So the thing is that, okay, so this is how I define operation. And then basically the state, how does the state change if I apply the operations? Then the local operation changes the state S to S prime, where S prime of x equals S of pi tensor Ix. Yeah, so let's define the notion of partial trace. So we have seen that, okay, how if I have an operation on one state, one register, how do I extend it to compound register? Now suppose if I have an overall state on A tensor B, how can I get a state which acts only over the first register, right? So let's see the notion of partial trace. So given a state S, from A tensor min B to C, okay, so define partial trace over B as trace B of S from A to C given by trace B of S acting on A equals S of A tensor I. So homework for you is to prove that S from A tensor min B to C is a product state if and only if S of A tensor B equals trace B S A times the trace A S on B, right? So the thing is that if you need to take a partial trace over a system B, then basically I can define a measurement, like I can define what it means to measure over the first register only, in which case I take the measurement operator on the second register as identity, right? So basically this allows me to define a state on just on A, right, by just taking always the measurement of identity on the other part B. And now overall you have a product state if and only if S of A tensor B acts as, you know, first I trace out B and measure A, and then I trace out A and measure B, and then I multiply the two. So this is for you to prove. Now we come to the notion of localized measurements. So what does it mean to have POVM measurements in the context of compound register A comma B? So let A1 up to AM in A be POVM measurements for register A, and applying to states S from A tensor min B to C, we get a classical outcome A. So we are only measuring the first sort of register here, and we are going to get a classical outcome K with success probability S of AK tensor I, and a new state Sk such that Sk of P equals S of AK tensor P over S of AK tensor I for all B in B. Right. So the thing is that if I have a sort of a measurement which is defined only over the first register, then I can just assume that over the second register I just apply identity, and the state which I'll get over the second register, that is defined as, like, the measurements for that state are defined by fixing the first value to be AK, which is what I have obtained earlier, and then normalizing the probabilities. Right, so this is how we define localized measurements on states in C star algebra. Right, so basically localized measurement, what it means is that what if you only have a measurement operator on the first register, how does it act on the overall sort of state? So this finishes the ideas of states, measurements, operations, partial trace and product states on sort of compound registers, and now we are in a position to understand what it means to have a perfect embezzlement in C star algebra model. So we'll look at that in the next lecture.